Good morning, everybody. We'll be having today's lecture only online, and I'll be probably using only 1 hour for the class. We'll have a 40-minute first session and then maybe a 20-minute another session. So this will be a short lecture for the day. So let's continue where we left the other day. So we were talking about typing again in terms of classes and objects and how they are related to typing. And the subtyping principle was such that if A and B, if A is a subtype of B, then an expression, an A expression that has A can be safely used in any context where B expression is required. So if you have B in an expression, you can actually replace it with an A, and this is the subtyping principle. So when we say an expression, of course, we are talking about, let's say, some sort of, let's say if we have a, let's say, some comparison, for example, let's say I am comparing an object of A with, let's say, with something, with an operator with, let's say, X, then, sorry, for B with an X, and this says that actually, okay, you can actually replace A here safely in this context. So this is the subtyping principle. Now, this is as far as the expressions are concerned. Okay, there are two other places where we need to actually define the subtyping, right? One is the subtyping for the function result. So this means that if I have a function that actually takes the domain C to A, and again, also another function that takes the domain C to B, then we can actually, as a function result, we can use B instead of A. Wherever B is used, we can use A. So if I have, let's say, a function that takes B as a something to as a result of this, that actually is going to generate a B value, B object, we can replace now this function's result as A as well. So this is what subtyping function result actually is saying. So another place where we'll need a subtyping relationship is as a function argument, meaning that if I am actually mapping A's domain to a C's domain to a function, meaning if I have B as an argument to a function, and that maps this to some other domain C, then we can use A in this and still hope to get actually the domain C. So this is the subtyping for function arguments, right? So this is not exactly, of course, now, if we think about what we have done in the past, as we talk about, let's say, typing relationship, we were treating everything as an expression, and an expression, if you recall, in the context of, let's say, a functional language or a functional programming language or imperative programming language, an expression was defined recursively, and you had operators or functions or values or sub-expressions that operators are working on. And there, a function argument is expected to have, especially a function argument, is expected to have an expression when we have pass by value, And then in the case of, let's say, a function result, the result of the function is used as part of the expression anyway. So that definition that we have for an expression was valid. Now we have two things going on. One is expressions kind of changed a little bit now because of the paradigm change or the change in our programming paradigm, right? So we are saying that programs are no longer expressions, only expressions, but some sort of let's say message to objects. When we talk about that, then an expression, a function result, and a function call and resulting of a function and a function argument actually changes meaning, right? So this is why we need to actually redefine function subtyping in this case. Now, once we have these definitions, now terminology, we have to introduce two more things to the terminology. One is covariance and contravariance. Covariance means that A and B implies that FA and FB is actually is true as well. So this meaning this is the a function that takes A and takes B, the same function that takes A and takes B, actually results in something that still the result of FA and FB can be a subtype. So covariance function application takes if A and B actually a subtype, FA and FB will be subtypes as well. This is important. This actually puts something on the function itself, meaning the function doesn't change the subtype relationship. So function result will be something else, right? So it will give you some other, let's say, object. That function will create perhaps another object, and the type of that object with the same function. When I have A or B as two different arguments, will actually result in subtyping actually will be preserved. The results of those functions will give you two different things, and the type of those two things will be subtyping, will have some subtyping relationship. And another alternative is, of course, is contravariance, where you actually change the order, meaning A and B, A is a subtype of B, but when I apply the function, the result is actually reversed, meaning FB becomes a subtype of FA. So this is a contravariance. So these are all definitions that might be useful in actually, let's say, designing and communicating the result of, let's say, of your design as a language. So covariance is going to be an important thing that actually, if you can, if your function definitions can, or a function, let's say, if those functions can, let's say, some functions might actually result in a covariance relationship, and some might actually result in contravariance relationship. And if you are able to actually keep these, this would be a good idea, because it will give you some let's say, way to keep track of the subtyping and you can subtyping relationships, and you can actually use those relationships for whatever FA and FB is doing. Of course, there might be cases, or there might be functions, and there will be functions that these two relationships are not going to hold. It won't be either covariance or contravariance. So this is a possibility always, right? So there's not limiting that. So you have an example here. If a circle is let's say a subtype of shape, then what you do is once you let's say what you can do is you can, if you have a let's say circle is a subtype of shape, then if you have a function that actually let's say take shape to circle, or circle to circle and shape to shape, or circle to shape, these will actually define these covariance and contravariance relationships. So if you have a function that actually takes the shape to shape, let's say shape to shape and circle to circle, then you have these covariance relationship, right? If the circle is converted to a shape and shape is converted to a circle, then they are actually that function is doing that, then you have a contravariance relationship. All right. So you can have covariance or contravariance relationships. Now let's look at actually with this information, let's look at Java types. We are gonna get a little bit details into Java types. So there are two general kinds of types in Java. These primitive types. These are not objects. Again, this is kind of a deviation from everything is an object, or everything is a, let's say, class type of let's say distinction. Here you have these primitive types like integers, booleans, etc., and they are not objects. They are treated as different types of primitive types. And then you have the reference types. Reference types are classes, interfaces, arrays, and so there is no, in this case, there is no syntax that actually distinguishes object star, object pointer from object. So this is what Java does. So reference types, referring to classes, interfaces, and arrays. So arrays are kind of treated differently, most probably because of efficiency concerns or something like that, right? Static type checking is gonna be actually a part of Java, right? Every expression has a type, and it will be the type of the expression will be defined or determined from its parts, right? So this is we have seen this one in other languages before. There will be some auto conversions allowed. Many casts are checked at runtime. So casting, some of the casting, or most of the castings will actually be checked at runtime. So this is not part of the static type checking. All right. So for example, if we assume that A is a subtype of B, if AX, if you define an X, if A and X, then we can use X argument to method that requires B. So this is the so if A is actually having a message with argument X, then X argument to method that requires, we can actually use X argument to the method that requires B, right? So B can be, this is the definition if A is of subtype B. If BX though, then can try to cast X to A. So if in this case, I can actually try to cast, this is gonna be you can try it, but at runtime, this will be checked, right? So downcasting checked at runtime, and it may raise an exception, so you may need to actually keep that exception somehow check. So just a pictorial representation of types in Java. You have the reference types and you have the primitive types. the primitive types, you have the Boolean, integer, byte, float, long, and so forth. And in the reference types, you have an object, starting with an object, and you have an object array. This is an array. And then you have the user-defined types, classes, and interfaces. And then you have another one that is actually over here. This is treated as another type, as a throwable object. And this is actually going to be used for exception types and so forth. So with regards to subtyping, primitive types can have conversions like, let's say, integer can be converted to long, and double can be converted to long as well. So there was possible. So there are some other possibilities as well for primitive types. In the case of class subtyping, which is similar to C++, subclass produces a subtype. This is clear. And in the case you have the single inheritance, of course, and then subclasses therefore forms a tree. Right. So the difference from the C++ is we have with the class subtyping, we have single inheritance. So in that case, your subtyping relationship will actually be forming a tree always. So there will be no graph, no things like, for example, something like this. So this is not going to happen with the classes. Of course, you have interfaces, and you can treat these as, you can see these as completely abstract classes. There are no implementations of them. And you can actually now create multiple subtyping with this way. Interface can have multiple subtypes. Therefore, you can actually have, again, here the importance is not in the inheritance part of it, but in the subtyping part. So from the user's perspective of the class, you have you can actually have multiple subtyping through these interfaces. Of course, this will be achieved through implementing and extending that interface. Now, arrays are covariant subtyping, right? So this is not consistent with the semantic principle, but array is actually, if you think of array as a function, then you have the covariant subtyping here. This is important. So how does Java handle class subtyping? The first thing that you have to have is this signature conformance. Subclass method signatures must conform to superclass. All right, this is one thing. There are several ways, actually 3 ways that a signature can change, can be different. One is argument types can change, return type can change, and the third one that we are going to be looking at now is exceptions. So the exceptions that a class actually that a class actually, or the method can throw can actually change the signature of a class. So we have been looking at these two for a long while now as a signature of a class or a function or a method. We look at the argument type, we look at the return type, but now we have to also look at the exception as well. What are the exceptions that are being thrown? And those must confirm. There has to be some conformance regarding those as well. So Java rule actually regarding these two things changed over time. Taking the, let's say, Java 1.1, arguments and returns must have identical types. This is what they actually have. So they look at these two first, and then they say you may remove the actual exceptions. So exceptions are not gonna be, let's say, you can remove the exception and you can still have conformance. And then in 1.5, they actually added this covariant return type specialization to the rule. Okay, so you see that actually the decisions are not that easy. There are a lot of things that you have to consider, and it may look like these decisions are somehow arbitrary, meaning why do I actually remove, let's say, exceptions? Why do I actually allow removal of exception? And perhaps at the time, maybe they were thinking that exceptions are actually kind of, let's say, not forced or enforced very strictly, and it will be difficult to actually match both argument types, return types, and as well as exceptions. And sometimes exceptions may not be implemented in properly or whatever. So let's look at the interface subtyping. We have seen this one or similar to this one before. You have interface shape. You have public method center and another public method rotate. And then you have interface drawable. You have set color and set, drawing. And then you have actually a class circle that implements both shape and drawable. Right? In this case, does not inherit any implementation. This is clear, but must define shape drawable methods. All of the methods should be defined and implemented inside the circle class. So with interfaces, it's clear that you can now actually have, let's say, graphs instead of trees as far as the subtyping relationship is concerned. So when you have, let's say, an object, let's say, a shape and a drawable, right? And when you have this type of thing, now you are actually adding, let's say, graphs instead of trees. So these are not anymore trees, but they are going to be graphs in terms of generalized trees or generalized graphs. All right. Of course, with interfaces, you don't consider the inheritance your main objective, and since you don't have anything from shape and drawable implemented, then this will actually not have any trouble of multiple inheritance that we discussed earlier. So the cost of this one is, of course, the offset in the method lookup table is not known at compile time. So this is an efficiency issue. So what Java does here is actually it has some different bytecodes for method lookup. One is when one method is actually when the class is known. When the class is known, then this is simple, right? When the class, when only the interface is known, what you do is when the class is known, then you don't need to actually do search. You can actually do the, let's say, do some sort of a method lookup at with an offset or something like that. But when the interface is known, then what you do is you search for the location of the method. The bytecode does that. And then cache for use next time this call is made. So this is the kind of the advantage, or let's say the speed up or efficiency that you can add. So when you have an interface, you know that you are not going to actually have a simple lookup table to find, or simple offset addition to find the code. So you have to do a search. This is similar to what Smalltalk was doing, but of course, Smalltalk was very general, and it was looking first to a method dictionary and then getting that method dictionary from there and then looking it up and so forth. So you can still actually optimize the search process a little bit better with the bytecode. And you can generate this bytecode as part of your, let's say, your loaded code there. And then, but one thing that you do is for the next time, once you actually find this out, so you keep another list, perhaps a bytecode actually keeps a list, maybe it's some sort of a symbol table now, right? And then you can actually have in that symbol table your method and then the address of that method for where you actually have the thing. So Smalltalk was not concerning itself with this one. Of course, Smalltalk could have done it as well, but then you have to have another, let's say, another mechanism to actually keep this one. So Java actually does that, and through its interface, through its actually interpreter, let's say, the bytecode can either search for the location of the method, and once it finds it, it actually will cache it, and then it will use that cached location for the next time. All right, so you can add again these additional, let's say, improvements to your language to make that, but this caching mechanism, of course, doesn't change the basic idea behind it. So it is still a dynamic lookup or it's actually a runtime lookup, and bytecode actually, the generated bytecode handles that. So array types are kind of treated a little bit different than the basic types, as well as the classes, objects, and they are automatically defined. Array by type T exists for each class, and interface type T. So it cannot extend array types. You cannot extend array types. Array types are final, right? And you might have multi-dimensional arrays and they are as the arrays of arrays. So you can actually have arrays of arrays, similar to perhaps the others that we have seen. So these are treated as reference types. Reference type, an array variable is a pointer to an array, and it can be null. Example is actually, let's say, circle array X, a new circle array size. And then you have anonymous array expressions like int, new int, something like this. You have Java allows you to do these type of things as well. Anonymous array expressions. So every array is a subtype of actually object array. Okay, so the length of array is not part of its static type. So length of the, so if you have, let's say, subtyping relationship, which you would have, let's say, circle, array circle, let's say, is gonna be a subtype of object array, right? So this is what it says. But the size information of the array is not gonna be part of its static type. So this is gonna be a dynamic part of it. So when we look at the static typing, we are gonna actually, so if we need some sort of, let's say, subtype relationship between an object array, between an array, some object array, and another object array, then size is not going to be an issue or the part of the static type checking. if there is anything done there. So the covariance relationship is gonna be the governing subtyping relationship for array. So if you think of array as a function, so then array, I mean, taking a, let's say, a class or taking an object and making that as an array means that you can treat this thing as a function. So I am functionalizing the array, and then that means that I am actually creating. So as when array function is actually used is going to be as this. This is a new type, right? And then T array is going to be is a function array. So array is a function that takes a type and creates an array type out of that. All right, and this is a function again, and then you have now a new type. So this is a domain that you are actually doing, and this thing is this function has a covariance subtyping relationship. So if you actually take the function, the same function, apply it to S and T, the result, the value or result of those functions are gonna have the subtype relationship. All right. So you can have some, let's check for some type errors. For example, I have a class A and I have another B that extends A, and I create a, let's say, a B array and an A array. Now, the question is, with A array, can I actually initialize it with B array? This says this is okay because B is actually a subtype of A. And then you can actually now, when you go back to A array 0 and you create a new A, this compiles, but at runtime it's gonna be checked because you are actually, this is gonna, there will be a storage issue. This will be actually a restore exception. It's not gonna work at runtime. This is a standard type error. So this covariance, really, I didn't talk about this when we talk about Simula, but this covariance for assignable cells is an import. I mean, we have to be very careful with this one. And so this is what the problem was that we were discussing. So this, let's say, covariance relationship, especially a function application and the resulting of that function and the subtyping of the results has to be considered quite carefully. Another type that we have for Java is exceptions, and this is similar basic functionality to the other languages. You have a constructor throw and catch exceptions, and you have dynamic scoping of your handler. Some specific things that Java actually does. An exception is an object from an exception class. This is what Java does. Java treats these as objects, and subtyping between exception classes are actually going to be there. You can use subtyping to match type of exception or pass it on. This is similar to functional programming in ML, pattern matching handler. So this is quite involved actually. This is a nice property. Type of method includes exceptions that it can throw, right? So let's look at this case. You have a throwable, and in the throwable case, you have exceptions. You have runtime exception and error. These are unchecked exceptions, and the exception itself needs to be checked, and there has to be a user-defined exception classes extending these exceptions. If a method actually, if a method throws if a method is possible, if a method possible throws a checked exception, then exception must be in the type of the method, and this will be now checked runtime at runtime. If you recall, for as far as the conformance goes, this has to be part of the runtime check of the subtyping. So one of the reasons that Java actually defines exception as a new type is because exceptions may contain data, and you may want to actually keep that data and process by the right, let's say, process it in the right way and communicate data in the right way. So class throwable includes a string field so that cause of an exception can be described, and you can pass other data by declaring additional fields or methods to your derived class. And you can use the subtyping relationship to catch the expressions. So you have a catch expression type, and so you have catch exception type, an identifier, and then this one. So the exception type here is going to actually look for the subtyping relationship. It will catch any exception of any subtype exception type and bind the object to that identifier. So if you have, let's say, prior to this one, in the block before this, if you have, let's say, there might be multiple exceptions thrown. So the one that actually is a subtype of this thing, then it will be actually caught, and the identifier is going to be actually associated with that one. That object, thrown object, is going to be bound to the identifier, and you are going to be using that identifier here to refer to that object. So when we look at the actual subtyping, we have these two things. We might have implicit subtyping, which will be a part of the dynamically typed languages. The relationship between interfaces is gonna determine substitution. Which one can we substitute with which one? And in the explicit subtyping is gonna be the statically typed languages. Type checker may recognize some subtyping. And one of the issues with this one is programming style implementation efficiency has to be actually handled here. And we talk about the covariance and contravariance type subtype relationship. And one thing that we have seen with there is a possibility, a problem with the Java array covariance, right? As if you think of array as a function, then that has a covariance relationship. All right. So when we just compare, let's say, C++ and Java, if class subtyping in C++, only when public base class is available or we used. Compiler allows subtyping with subtyping and covariant subtyping. And in the case of Java, it actually uses, it can allow this when you use extend, and it can also allow you to have covariant depth subtyping as well. All right. All right. So it is 40 minutes now. Let's take a break, and we'll continue in 10 minutes, 9:20, with the Java language implementation details, specifically Java virtual machine, method lookup. We discussed this one a little bit. Some sort of verifier analysis, and optimization of method lookup, and then security issues. I'll see you in 10 minutes.